So you've probably noticed that in the last few months, I've been posting a little bit more often about modern climate change as opposed to my normal ancient climate, ancient life, ancient geology type content on this channel. That's because I was teaching a more modern climate related class this semester, and I know I said in the last climate related video that it was my last climate related video for a while. However, I noticed with both my students and viewers online, there were very common overlapping misperceptions about climate change that I just want to take the time to clear up in this video, because otherwise I'll just be responding the same thing to the same question over and over again in my comment section. So instead of doing that, I'm just going to answer all of these questions, or at least the top 5 most common questions or misconceptions I see about climate change in this video. So let's get started. I think the thing that I see most commonly, because I talk about climate change throughout Earth's history, is the argument that the climate is always and has always been changing throughout Earth's 4.5 billion year history. So there's no need to worry, just go with it. It's supposed to happen. However, when we really look into Earth's history, we see that nearly every time the global climate has changed at a rate as fast as today's rate of change, it has caused a mass extinction. For example, rapid global cooling and/or warming at the end of the Ordovician period around 445 million years ago, the Devonian around 365 million years ago, then the Permian with the Great Dying, the Triassic, and of course the most famous dinosaur extinction at the end of the Cretaceous around 65 million years ago. These events mark the big 5 mass extinction events, or the largest 5 mass extinction events of our current Phanerozoic eon, that is the last 540-ish million years. And we are now in the 6th mass extinction of the Phanerozoic eon due to our current warming trend. No matter the argument of what the cause is, even though we know the cause, no matter that argument, even if we take that out of the equation, we know that current rates of extinction, current rates of warming and extinction are on par, if not greater, than a lot of these big 5 mass extinction events. That said, we know that major global widespread devastation of life is and will continue to happen throughout this event. So really, we can think about it this way. If the dinosaurs could have stopped the asteroid that led to their extinction, or at least their non-avian extinction, they would have probably at least tried. And this is the situation we're currently in. We can stop our own extinction, but we have to work together globally, and that's not our strong suit. I think it's harder because obviously it's not a physical thing that we can see coming like an asteroid. It's more of here's a projection based on a model of what the climate's gonna be like and what kind of devastation that will cause. And that's harder for people to visualize and understand than look, asteroid, you know? But yeah, that's number 1, is the climate's always changing. It's always changed. We'll just adapt to it. No, it has always changed, but when it changes super rapidly, obviously it causes mass extinction, and we're in that situation now. Now, some of you might rebuttal this by saying, okay, rapid climate change at a certain magnitude causes mass extinctions. Sure, but why didn't then the PETM, the Paleocene-Eocene thermal maximum, cause a global mass extinction if it was rapid global warming at a magnitude on par with the Big 5? Well, it was a rapid spike in warming. You can't really see it in this graph because of the temperature, color coding that's going on with the bars here. But there is a rapid spike of warming at the Paleocene-Eocene boundary of the timescale, and that's about 55 million years ago. And this spike of warming was very rapid, and it did cause massive devastation among many groups of organisms. That said, it wasn't on par with the Big 5 mass extinctions, but this brings up an important point about our current extinction event and current global warming trend compared to the PETM, and that is we have to take into account not only the rate and magnitude of global change that is warming or cooling, but also the type of life that is around during that period. So in the Paleocene and moving into the Eocene, we can see that the climate was a global hothouse. That means that there were no ice at the poles. It was a lot warmer than it is today in our current ice house climate. And so life here, because this happened gradually, all of these changes are gradual compared to the big spike at the PETM, life was adapted to warm conditions. That is, life was warm adapted and therefore could handle a warming event relatively better than life today, which is cool adapted. We all evolved in an ice age. We're still in an ice age, which is another misconception that I'll get to later, at least misconceptions surrounding our current ice age and how it works, but I'll get to that. We have evolved in an ice age, in an ice house climate, that is with ice at the poles. We're used to this relatively, cool Earth relative to the Paleocene and Eocene climates, and we are what we call cool adapted species for the most part compared to the Paleocene and Eocene species. And that means that a warming of the same magnitude of rate of the PETM, which is what we're seeing today, will be much more devastating to current modern life on Earth because it's cool adapted compared to warm adapted. This is just one more aspect that we have to look at when we're trying to understand whether a certain warming or cooling event and its rate and magnitude will affect life and how it will affect life on Earth depending on the life that's present. Which brings us to misperception number 2, which is that we are currently in an ice age. Earth is not warming, and or that it's a good thing that we're warming because who wants to live in an ice age? Well, there's a few things wrong with this thought process. One, I do have to just confirm, yes, we are in an ice age. And currently we are and have been in a natural interglacial period of, relative warming throughout that ice age. All that means is that in our specific ice age period, which has been going on for the past 3 million years-ish, 2.6 million years, Earth has been undergoing glacial expanse and retreat through interglacial cycles. That is, because Earth's orbit and other astronomical features like its tilt and wobble, because those things change in a periodic cycle, this causes interglacial cycles of glacial expanse and retreat, bringing us to where we are today. And we are, yes, in a natural interglacial of warming within our current ice age. However, we humans are now adding on to this natural cycle of warming with unnatural warming from our activities at a rate that is too fast for organisms to adapt. Again, throughout Earth's history, we see that when climate change is gradual over geologic timescales, millions and millions of years, life typically is fine. There's no big mass extinctions or anything. But when it's rapid, when it's at a rate that life cannot keep up with evolutionarily and adapt to, then it becomes really devastating to the life that cannot adapt quickly enough. And that's what we're dealing with today, and that's what happened throughout the big 5 mass extinction events. That's another misconception that I don't even think I listed in this top 5, and that is, well, temperatures on Earth were way higher in the Mesozoic when the dinosaurs roamed the Earth, so why didn't they all die? Because Earth was too warm. It's not that Earth can get too warm for life or too cold for life. It's just that rapid change, rapid warming, rapid cooling, rapid change is what is devastating to life. At a short geologic period, rapid global change is what is devastating for life. It's the rate more than the magnitude. The magnitude matters, but the rate matters arguably more in terms of causing mass extinctions. Anyway, I'm getting on a tangent. For this slide, we are focusing on, yes, we are in an ice age, and yes, we are in a natural warming of that ice age, a natural interglacial. However, we are adding on to that natural warming with a spike of very rapid unnatural warming due to human activities. And again, the fact that we're in an ice age definitely does not mean that it's good that the Earth is experiencing warming. It actually makes things more potentially complicated and more devastating, again, like I mentioned earlier, because we are cool adapted, because life that is present on Earth today evolved in an ice house climate. Therefore, if we drastically warm the Earth now, life will need to adapt quickly to more warm conditions, which might not be very easy for the current species that are living. Another common comment that I see kind of related to this, oh, it's good that we're experiencing warming, is that more CO2 in the atmosphere equals more photosynthesis, which means more biodiversity, and therefore that's a good thing. However, this isn't necessarily the case when CO2 is rising so rapidly that life cannot evolve to handle it and adapt as ecosystems to handle that. For example, humans wouldn't immediately thrive if we were flooded with more oxygen unless we were given time to slowly adapt to that. The rapid increase in CO2 is also altering the balance of ecosystems, allowing some species of plants and trees to take advantage of this influx of CO2 over others, and this is causing domination of certain ecosystems by one particular species or one group. A lot of times because of our own actions, it's invasive groups, and this is kind of leading to lower biodiversity in these ecosystems because the diversity is being taken over by just this one group dominating. It's also important to note that more CO2 doesn't always equal more photosynthesis or more productivity in plants and photosynthesizing organisms, because CO2 is rarely the limiting nutrient for plants and other photosynthesizing organisms. In other words, CO2 is abundant enough that the plant would grow given its provided other nutrients that are often limiting nutrients. Limiting nutrients just refers to the nutrients that are limiting the growth of that organism or plant. It is typically phosphorus or nitrogen or potassium or iron that really increase plant or photosynthesizer growth, because those are typically the limiting nutrients in the environment, especially phosphorus and nitrogen. If you add more phosphorus and nitrogen to an algal bloom or to plants or whatever, they'll typically grow more because that's what was limiting. That's why fertilizers are made with all of these compounds. However, that said, even if we assume that all trees would just increase their growth and productivity due to increased CO2 in the atmosphere, this can't necessarily happen when we're cutting all of them down. And now on to misperception number 3, and that is warming causes CO2 increase, not the other way around. Yes, that's right. A lot of people argue that it is not increased CO2 levels that cause increased greenhouse effect, which cause temperature rise, but rather temperature rise leads to CO2 increase. And what do you know? It's true. It actually works both ways. And this is called positive feedback loops. In the climate system, there are what we call feedback mechanisms, which can be positive, which can exacerbate the current trend, or negative, which balance out the current trend. So an example of a positive feedback loop would be global warming causing ice to melt, which lowers Earth's albedo or solar reflectivity. In other words, more solar radiation is absorbed by Earth's surface, and therefore Earth heats up more, and therefore more global warming occurs, and this kind of just leads to an exacerbating or worsening effect of that current global change. Likewise, this can happen the other direction. If global cooling is going on and ice is forming, this increases Earth's reflectivity, or albedo, which increases the cooling, and so on and so on. These positive feedback mechanisms can lead to what people sometimes call runaway effects or runaway climate change. That said, there are many negative feedback mechanisms, which I've talked about in many of my videos, so I won't go into it here. But another example of a positive feedback mechanism that leads to this particular misperception is that melting ice also releases stored methane and CO2, which increases greenhouse gases in the atmosphere, exacerbating warming. That is, warming causes ice to melt, which releases greenhouse gases, causing more warming, and so on and so on. That said, it can go the other way. Increased human emissions of CO2 cause warming, which can cause more melting and cause more methane and CO2 release. So it can start with CO2 causing warming, and it can also start with warming causing CO2. Throughout the Ice Age and the interglacials that we talked about for the past 2.6 million years, These cycles have been driven by temperature first, CO2 second. Why? Again, like we talked about earlier, the interglacial cycles are driven by astronomical changes, so cyclic changes in Earth's orbit or wobble or tilt. And then these temperature changes, the temperature increases and decreases, these are what caused the CO2 concentrations to then follow the temperature trend. Because as temperature rose, more CO2 and methane were released from melting ice, and as temperature fell, more was trapped in the ice. The current human-caused warming trend is the other way around. It's CO2 first, exacerbating the current warming because of the greenhouse effect, which is leading to more melting and increased carbon in the atmosphere again, and thus more warming. So the positive feedback mechanism builds on itself, but it can start from anywhere in that circle. It can start from the warming, and it can start from CO2. They cause each other. Moving on now to misperception number 4, and that is CO2 is not building up in the atmosphere. It's actually all going into the hydrosphere and biosphere, that is, oceans and other water bodies, and trees and other photosynthesizing organisms. This is one, not entirely true. Yes, a lot of the carbon dioxide we're releasing does go into the oceans and the trees and the other photosynthesizing organisms. However, there is still a buildup of carbon in the atmosphere, and it is a net positive buildup in the atmosphere. That means that the amount of carbon going into the atmosphere adds up to more than the amount coming out of the atmosphere. Thus, carbon dioxide concentrations in the atmosphere are increasing every year. And these numbers don't even count what we're releasing that goes into the other spheres, that is, the hydrosphere, the oceans, and the biosphere life. That said, it's not necessarily a good thing that a lot of the carbon dioxide we're releasing is going into the oceans and into life and trees and whatnot, because this doesn't bring back balance to the perturbed or altered carbon cycle, because we're not originally getting the carbon from the hydrosphere or the biosphere, we're getting it from the geosphere, in other words, rocks, fossil fuels. And so to bring back balance to the carbon cycle, we would technically need to put it back into the geosphere, not the oceans and the trees. And also, when it goes into the oceans and to algal blooms and other forms of photosynthetic life that are increasing in productivity due to increased CO2, it causes ocean acidification, eutrophication, and harmful algal blooms, as well as harmful ocean anoxia, or a lack of oxygen beneath those blooms, which kills marine life, which all life relies on. And so we really need to sequester it from the atmosphere, hydrosphere, and even move it from the harmful biospheric sinks, like certain types of algal blooms and whatnot, into healthier biospheric sinks, like trees, soil microbes, and seaweed, like I discussed in my recent climate change solutions or carbon sequestration video, which I'll link up here for you if you're interested. That video goes over exactly how we can sequester carbon into the biosphere and how we can accelerate our sequestration of carbon into the geosphere or rocks for long-term storage and to finally balance out our current perturbation of the carbon cycle. Which brings me to the final misperception that I'll talk about in this video, and that is that we need to save Earth. I've talked about this in a short that I did, which I'll link up to the top right if you're interested, but although the term save Earth is typically well-intentioned, it miscommunicates the problems associated with climate change by implying that if we don't do something, Earth will somehow come to an end. But Earth will be fine. As we talked about earlier, it has gone through major climate changes and mass extinctions in the past, and it will get through this one. What will be affected by this current 6th mass extinction isn't Earth itself, but the life that is on it. Yes, life as a whole will go on. Not everything will go extinct. Well, probably not. But it will look very different than the current biosphere, as we've seen with every single era in Earth's history, all of which have ended in massive mass extinctions. the current one that we're in, the Cenozoic, hasn't yet, but it's looking like it will. But the Paleozoic era ended with the Great Dying, the end Permian mass extinction, which caused 96% of species on Earth to go extinct. And then we had the Mesozoic era, which took out our favorite non-avian dinosaurs and caused a major shift in the biosphere. And obviously now Cenozoic era life looks way different than these ancient life forms look. And so, yeah, life moves forward, and that could be seen as a good thing, but you just kind of have to make your choice of whether you want to be part of that next biosphere or not. So essentially, what we mean by save Earth is really, when we get down to it, save humans, or at least the current biosphere that supports human life. Hello, Editing Rachel here. I wanted to chime in and explain, because I forgot to explain this in the video, but I wanted to explain why this last misperception can be problematic. Because again, like I mentioned, the we need to save Earth sentiment is typically well-intentioned. However, it could fuel ideas in people's head about, you know, whether we should spend our time combating climate change here on Earth or terraforming another planet like Mars to live on. It's these kind of ideas that Earth will come to an end and we need to spend our time elsewhere that aren't the best, because they're not true. I mean, we know that obviously Earth will not come to an end, and of all of the planets that we have at our reach, Earth is by far the most terraformable from its current state as well as where it's heading. You know, yes, it's not heading in a great direction currently based on climate change. However, it's not going to come to an end, and it's still way better of an option than anything else out there. And before you go and tell me in the comments that nobody is gullible enough to believe that the Earth will actually come to an end if we say things like, we need to save Earth, let us not forget that the history of humankind's understanding of climate science is not great. We all remember the snowball incident. So I hope this video helped clear things up for you. I know that for me personally, I also had most of, if not all of these misperceptions about climate change before I started, learning more about it, doing the research about it. So I also was wondering these things whenever I would hear anything about climate change. And it was really clarifying for me when I did learn about these concepts. And I hope that this video was kind of that for you, or at least helped a little bit. So with that, thank you so much for watching, and I'll see you guys next time. Bye.